Hello students, welcome back. We completed up to example 4.6. Remember these examples? Express it as a Riemann sum. 4 rectangles, so 4 things have to be added. Width times height. Width is 4, the same, and heights are f of -2, f of 2, f of 6, and f of 10 respectively. Another example here, again 4 rectangles with even width. Width is 4, identical, and heights are given by the left-hand side, -4, 0, 4, and 8 respectively. Here's a little bit more general example. We have uneven width, and widths are 1, 5, 7, and 3 units respectively, and heights are given as function values as -4, -2, +5, and +10 respectively, so that we get this kind of Riemann sum. You can do this kind of thing for any graph with any number of rectangles. I gave you 4 rectangles here, but I could have given you 6 or 7, up to 10 maybe, but if it exceeds 10, then too tedious. But theoretically, I can do that for hundreds of rectangles. Those are Riemann sum problems. Now let's do Riemann integral problems. How about these? We have limit of some Riemann sum, and they should correspond to this. Compare this with these. Do you see the resemblance? Maybe not yet. I'll give you a hint. So this can be rewritten as copy and pasting and moving this 1 over n to the right, and I'll make sure that we have multiplication first before the summation. Does it help? Maybe not yet. One more hint. N is going to infinity versus 1 over n going to 0. Now compare this with that. Do you see a resemblance now? Delta x going to 0 versus 1 over n going to 0, and delta x 1 over n that shows up right here, as I just highlighted in blue right here. Maybe a little bigger font will be helpful. So look at blue, delta x here and there. 1 over n here and there. See the resemblance? And then I is running from 1 to n, k is running from 1 to n. Just a choice of character, no problem. And sine of k pi over n, that's gotta be yk star. As a matter of fact, let me make one more adjustment here. Instead of y star I, let me rewrite it as f of x star I, because any yi star can be rewritten as a function value f of xi star whenever we have a continuous function. Remember this? Riemann sum for continuous function yi star can be rewritten as f of xi star, as you can see from this visualization. Whatever y value we can associate with a certain function value, like this, like that, like this. Here's another candidate, but I can select any one of them. If you have discontinuity, not in general, but we don't have to worry about the discontinuity in this particular case because we have a sine function, no problem there. Exponential function, again, no problem. So we can always rewrite into f of xi star, or in this case, xk star. So, do you see the resemblance? This yi star, which I just highlighted in red, or f of xi star, which I just highlighted in red, should correspond to this one here. Okay, and then what? If you can go from this point on, stop the playback and go ahead. It's going to be a challenge, but you should be able to do it. Now, if you get stuck, then I'll give you one more hint. Now, this hint is going to be critical. It doesn't always work, I have to say, but most of the time it works. Use k over n. You have to have a k expression, so some k expression is necessary, but most of the time it's k over n. We need n down here, as you see down here. How does it help? Consequently, I can rewrite x as k over n, and x replaces k over n here, so my function is going to be sine of pi x. You see, pi is still there. K over n becomes x. So it's not just sine of x, but sine of pi x. Let's make this observation. This is a key technique. It doesn't always work, I have to agree, but most of the time it works. And once you make that assumption, you can find the integrand easily. And 1 over n, that's going to become dx. Delta x going to 0, so delta x is going to become a dx. Here's my function, the integrand. So we're going to get appropriate integral expression. And then my function is sine of pi x. Okay, all right, sine of pi x. Let's highlight this in red. And then n1 over n is delta x, so it becomes dx, the infinitesimal. All right, if I find out a and b values, then I can get this as an integral, and then I can apply the fundamental theorem and go ahead. How to get a and b? Well, those are starting and ending points of x. And please note that k begins from 1 and ends at n. Do you see that? So when k is 1, then x is k over n, which is 1 over n, and that's going to 0. Do you see that? Let's highlight this in green. And that's going to be the starting point right here. All right, what's the ending point of this x value? K goes from 1 to n, so n is the ending value of k. So x is k over n, and that's n over n, so that's 1. Do you see that? Let me highlight it in purple. And this one here, consequently, is becoming 1. Maybe a little bit bigger font will be helpful. So what did we get? We get this integral computation. Calculating this integral using the fundamental theorem, that should not be too much of a problem. So rewrite this integral into a Riemann sum form. Instead of n going to infinity, you can rewrite it as 1 over n going to 0, and 1 over n is your delta x. And your function, okay, that's a bit tricky part. You can put x as k over n. It does not always work, but most of the time it does. And there may be some exceptional case that you have to work out for something else, but those are really rare. Anyway, if you make this assumption, x as k over n, everything fits into piece from this point on. If a problem is well-designed problem, easy enough, that is. So pi is still there, so sine of pi x, okay, that's my integrand. K begins from 1, so x begins from 1 over n, that's going to 0. K ends at n, so x is n over n, that's 1, so integral 0 to 1. And calculating this integral using the fundamental theorem, that should be easy, so that's left to you. What if I, oh, by the way, here is a visualization associated to this. It's a Riemann sum given by right-hand side endpoint. So it's a Riemann sum, and limit of the Riemann sum is Riemann integral. What if I change this problem a little bit to this? K starting from 0 to n minus 1. Still n rectangles. Will that change a lot? Not really, because if k is 0, then we have 0 over n, and that's equal to 0. So starting x value is 0 again. K is ending at n minus 1, then k over n is n minus 1 over n, and that's going to 1. So 0 to 1, the same as before. So whether going from 0 to n minus 1 or 1 to n makes no difference in the end. Now, how about the second problem here? Stop the playback and try. Do you see that we have similar situation, except that we have exponential function instead of sine function? So that this one here is actually e to the k over n, so that's e to the x power. So k of n becomes x, so your function is e to the x. How about the starting and ending point of the interval? K begins from 1, so k of n is 1 over n. That's going to 0, no problem. But in this case, this goes to 2n instead. So when k is 2n, we have k of n is 2n over n, and that is 2, not 1. So this integral runs to 2. Calculating this integral, that's a piece of cake. Just apply the fundamental theorem and get it done. So a little bit more expanded form, but the same. Get this assumption, k over n, and get your function. And the starting k value and ending k value will give you the interval. There you go. Both problems completed in the same viewing window. That completes section 4. See you in section 5.